So I wanted to give some background on the force and torque on a closed current loop that's subject to an external magnetic field. Okay, on the left side here, we have that closed loop of area A times B, as shown, and the current in it is moving counterclockwise, right, through segments 1, 2, 3, and 4 as shown. Just assume it's hooked up to a battery somehow and it's allowed to freely rotate in space about an axis, well, in space. You'll see how it rotates shortly, okay? If the magnetic field is moving from left to right horizontally, there are two magnetic forces on it, okay, causing a rotation. And the only segments of this loop that there's a force on are the segments where the current direction and the magnetic field directions are perpendicular. In other words, sections 2 and 4, right? In section 2, the current is going down, okay? So remember, magnetic, whoops, I had another setting, let's go there. The magnetic force is equal to QV cross B, or you can also write this as IL cross B, okay? Using the right-hand rule, right, where you use, say, the pointer finger for the first vector and then the middle finger for the second vector, means that your thumb is in the direction then perpendicular to both of those, and that stands for the direction of force. So if you put your pointer finger in the direction of L, in other words, the direction of that current, well, that's pointing down, right? Down that way. At the same time, maintaining that pointer finger direction, if you put your middle finger in the direction of the magnetic field to the right, that means, using your right hand, of course, that means that your thumb is pointing out of the page. So for, we'll say, FB2, that is going out of the page. Circle with the dot. On segment 4, that pointer finger now points up. The magnetic field still points to the right, so now you have to kind of rotate your hand around, maintaining those two directions, right? It's okay to turn your body and contort your right arm. Now your thumb will be pointing into the screen or into the page. So over there, we have force B, I'll call it 4, into the page, right? X. For 1 and 3, right, they cancel because the current and B are anti-parallel. When you evaluate this cross product, the sine of the angle, sine of 180, is 0, right? So those two magnitudes cancel. Thus, there are only two forces on it. So FB2, the direction was, well, we'll say the magnitude is equal to ILB, and the direction is into the page. Sorry, for 2 was out of the page. For FB4, the magnetic force on segment 4, that magnitude is the same, ILB, but now it's into the page or into the screen. And so if you add up all 4 forces, technically, right, you'll get 0. The net force is 0. And this is true in all cases, right? For a closed current loop subjected to an external magnetic field, the net force is 0. So what does this mean? It means that it will not, the center of mass of this loop will not move in space. The center of mass will not move in space. However, the actual object may move in space, and in fact it does. It rotates about an axis. There's an axis about the center, right there, the long central axis. You can say at a distance of, what is that, B over 2. So that's what it rotates about. And so it goes, I'm really running out of room here, but it rotates around. Okay? Looking on the right side, this is kind of a top-down view, or rather, let's see, an underside view. So if you were to take the top and move it down, and take the bottom and flip it up, this is looking from the bottom up of the left-hand picture. Okay, the right side is, this is segment, where was it, 2. This is segment 2, and the right side is segment 4. Notice the circle and the dot right there. Circle with the dot means that current is coming towards you. And if you were to look kind of from the bottom up, that I2 would be coming towards you. And this cross right there means that the current direction is into the screen in that direction. So if you're looking from the bottom up for the current through section 4, it's going away from you, which is what that means. Okay, so the bottom up. It's rotating, which means that there's now a torque, right? You can have a torque without a net force, right? So let's take a look at what the torque will be. Thinking back a couple chapters, or really a couple months, torque is always, whoops, no cross yet. Torque is always equal to R cross F, right? Whatever the lever arm is, in other words, the distance from the axis to where the force is applied, that's R, and then the force is, well, whatever the force is. In this case, it's the magnetic force. So let's see here. Remember that you can evaluate the magnitude if you wanted to. That's RF sine theta. Okay, but for right now, let's take a look at the two torques we have, because we have two forces. All right, we have a torque due to segment 2. Right, that force is, well, upwards, which kind of makes sense if you're looking from the bottom down, right? R, in that case, from the axis to where the force is applied, is right there. Okay, that is our, we'll call it R2. And so if we were to cross that with F2, using your right hand, putting your pointer in the direction of R, and your middle finger in the direction of F, that means that there's a torque, or your thumb should point, should point, I'll say, into the page. So let's do this. For torque 2, that is also into the page. Nope, I'm totally getting this backwards. I apologize. Torque 2 should be into the page, which is that. Okay. Now, let's add that to our other torque. We'll call it torque 4. Torque 4, the radius is from the axis to where the force is applied, right? That's R. So point your finger in that direction, and then your middle finger in the direction of F4. 1, 2. All right, so now your thumb should also be pointing. I'll do it here. Whoops. Now your thumb should also be pointing into the page. All right. If you need to, pause this video and try it for both cases. Your thumb should be pointing into the screen in both cases. The net torque, remember, is equal to the moment of inertia times alpha. So there would be some kind of angular acceleration, right? But we're not necessarily worried about that. We're worried about what the actual torque terms are. If they're R cross F, what's this R distance, right? What is this? Let's do it right there. What's that distance? Well, if that entire length is B, and going over here, I'll erase my arrows over there, that entire length is length B. So from the axis to the end, well, that's B over 2. So we have B over 2, okay, times the magnitude of the force, FB. What's the magnitude of the force? We found that on the left side. It's IL. In this case, L is our length A. Okay. I'll write this I as L, right? That's A. Because remember, that's the length through which that current is traveling. And then we have B, right? And then the sine, of course, the sine of the angle in between R and F. R and F, well, that can change, right? For the general case, we'll leave that as the angle theta, okay? And so this was for segment 4. That was B over 2. It turns out that it's really the same thing for segment 2, right? It's the same thing for segment 2. So I'm going to take this and multiply it by 2. And so we see that the torque is equal to I times AB times the magnetic field, the capital B, and sine theta. Okay, so that's what our torque is equal to. AB, well, that's simply base times height. So we'll call that capital A for an area, right? Capital A. And so we can write this torque in general as another cross product, right? Let's effectively go backwards from magnitude to vector. Now we have current times the area crossed with magnetic field, and the only thing that's a vector is the area and the magnetic field. And that is our expression, well, vector, for torque, right? And you can notice the area vector is perpendicular to the face of AB, right? So that's torque. Thanks for watching.